Everybody. My name is Matthew Guzdial. Oh, thank you. I'm an assistant professor here in the CS department. I'm also a Canada C4 AI chair with Amy. I am a substitute. I do apologize if you saw originally you signed up for this. You said, oh, it's Anurag Sarkar. I love that guy. Famous Anurag Sarkar is my postdoc, but he got sick. And so rather than have us cancel 2 weeks in a row, I took on the challenge of making slides in 2 days. Anyway, so today I'm going to be talking about true novelty and out of distribution generation. And then I have a subtitle through procedural content generation via knowledge transfer. So I'm going to talk about these things in order. First off, what do I mean by true novelty? This is a wildly subjective thing, and there's a lot of debate around this. So I will note that I am massively impacting my understanding of novelty here from the computational creativity community. This is a community that looks at sort of defining what do we mean by creativity? How can we represent that computationally? A huge name in that area is Margaret Bowden, visualized here. And she has this really cool concept of P creativity versus H creativity. P creativity is personal or psychological creativity. So we can define this as novel, valuable, and surprising information or something to an individual, right? So like a child will often go like, oh my God, that's wild and so cool, because they just have a limited understanding of the world compared to if an adult see the same thing, probably less exciting, right? That's the sort of idea there. There's H creativity, which is historic creativity. This is novel, valuable, and surprising to history. This is a undefinable thing generally, because we do not have an objective, full understanding of the entirety of history, unfortunately. But it's useful as a theoretical lens in terms of understanding concepts like novelty, right? So throughout the rest of this talk, I'm going to be sort of leaning or have the goal of H creativity, but we're also often going to measure that in terms of P creativity, the understanding of a particular system in terms of what is novel, what is valuable, what is surprising. Okay, so and then what do I mean by out of distribution generation? So if we imagine that we have like a learned distribution, unfortunately my title's slightly cut off, hopefully it doesn't keep on coming up. We can imagine like, for example, MNIST. This is just a VAE. I just trained this up for the purposes of this slide. It's a super simple two-dimensional VAE, so I can literally represent the latent space, right? If you're not familiar, MNIST is a data set of a lot of hand-drawn digits, right? So that's literally my latent space. It's literally the latent space that we would learn if we were trying to like generate new hand-drawn digits, right? You can see actual hand-drawn digits there, and then things that are like sort of in between them, right? So this is the distribution. This is the distribution for MNIST, for this particular learned distribution. Now, what if I wanted to find this image of the dog inside this distribution, right? Doesn't work. It doesn't matter how hard I look. I will never find this image of a dog in this learned distribution. That would be out of distribution, right? Make sense? Now, I can get close. I could approximate it. Maybe I have like a little, white figure that has like the outline of the dog there, but I'm never going to find the dog. And then you might say, well, why does this matter? Well, modern AI systems are actually pretty awful at out of distribution generation, or generally out of distribution dealing with anything. It's a big problem. So let's say you wanted to use machine learning to capture a radically distinct art style, or maybe you wanted to use machine learning to create something with no historic data, right? Or you wanted to use machine learning to answer an unanswerable question, right? Good luck, right? Like you have no options here. So dealing with things that are out of distribution is actually super important to a lot of like real world problems. Let's go with a completely non-real world problem for the purposes of an example. So let's say we wanted to come up with a brand new cool unicorn character. And let's say we had two different scenarios here. One that we can think of as being rather like low novelty and one that's a bit higher novelty. So we have our low novelty example here, a standard fantasy unicorn who hangs out in a field. Not really all that exciting, right? There's been a million My Little Pony shows. The second one, an action hero cyborg unicorn with a red cape and a sword for an arm. Slightly more novel conception of a character here, right? So we can feed prompts related to these to like something, for example, like DALL-E 3, just an open source version of it. If I want a unicorn in a field, no problem, right? This is complete within the distribution. There's lots of examples of this that it's been trained on. Easy peasy, not a concern. Don't pay too much attention to the joints on the unicorns. Otherwise, we're fine. Now, if I want my more quote unquote creative unicorn, it sort of works, but it's still not quite there, right? So we'll note I wanted a cyborg unicorn. At most, we have sort of like unicorns wearing armor or maybe a robot unicorn. I wouldn't really call these cyborgs. That's obviously subjective, though. But I also notably said that we had to have a sword for an arm, and that didn't really work at all. It was like, oh, you mean a hand holding a sword, right? You surely don't mean a sword arm. What is that? That's nonsense. It doesn't really work. Okay, so what do? Hopefully I've now convinced you at least a little bit that this is a thing that matters. What can we do about it? And today in this talk, I'm pitching you on PCG-KT, Procedural Content Generation via Knowledge Transformation. This is a recent survey paper on this sort of problem. We also defined this framework in this recent journal paper. Basic way this works is we're going to say that we have this framework for understanding how you can transform knowledge so that we can do out of distribution stuff, right? So we're going to have some initial raw knowledge that's over on your far left here. In this case, this is like a tile or text-based representation of a video game level. I do a lot of work in games. Then we extract some knowledge from it. So for example, here, this would be like some sort of like Bayes net or Markov chain or something like that. We're extracting some knowledge directly from this information using some sort of training process. Then we have some transformation function. The transformation function is going to change the extracted knowledge in some way. So initially we had some distribution. We're now going to run this transformation problem to try to get a new distribution out of that. That gives us this K transformed, and then we can get new content out of it, right? Where this new content is out of distribution from the original derivation function, the original thing that we extracted knowledge from. Does it make sense? Sure, good. Yeah, totally. We'll get to that to the upcoming slides. No, it's fine. So in the original paper, we identified two major approaches to this. We talked about transfer learning. We talked about combinational creativity. So I'll go through each of these in turn. Let's start with transfer learning. So if you're not super familiar, the most basic version of transfer learning looks a little bit something like this. We have some source data set or source environment, if you like RL, like a bunch of people here do. And then we're going to use that to train some initial model, right? Then what we're going to do is we're going to transfer the parameters of that model, whether they be neural network weights, whether they be like probability distributions for a Bayes net, it doesn't really matter. We're going to transfer them into some secondary model, which looks exactly like it initially. We're going to continue to train that on some target data set or environment, and thus way we're going to transform it to be able to get new stuff, right? So for example, I could have my source data set be all these pictures of anime faces for some reason. Let's say I'm training like a VAE or something. And then my target data set is like pictures of Pokemon, for example, right? You'll note here the sort of important bit, the case that we care about when we're doing transfer learning, is the relative size of the data sets. We're generally assuming that our source data set or source environment, we can get a lot more data out of that compared to the target environment, right? So if we just train on the target environment by itself, it wouldn't really help. Let's look at an example of that real quick. So this is some work from one of my prior students, Adrian Gonzalez, attempting to like represent Pokemon. We have the actual Pokemon in a sort of lower resolution on your far left over here. But over here on the right, we can see various differences. This one over here is if we do that transfer I just mentioned. So we sort of pre-train on these like anime face data set. If we don't do any transfer, we can see we can get in like this region over here where it's way worse. So the idea is that with transfer learning, we can like learn some good local features and then reuse them based on some target data, right? What does this have to do with out of distribution generation? Let's take a look at another example of that. So this is some work by my buddy Sam Snodgrass while he was doing his PhD at Northeastern. So what he did was he trained an initial Markov random field, which is an older probabilistic graphical model approach, still very helpful in a lot of cases, but less popular these days, which was originally trained on Mario levels. And then he continued to train it on Kid Icarus levels, right? Over here, we can see an example of Kid Icarus level. And if you know anything about Mario, and if you know anything about Kid Icarus, the output levels that you get from that do not look like either of those. They are wildly weird and different, right? So they're out of distribution, right? These are different than what we had before. Now, to Russ's question, is this valuable? I have no idea. This would depend on how we define value, right? We'll get to something that's closer to trying to get value out of that in just a second. And there's another example, but this one for Kid Cool. I put this one second because no one knows what Kid Cool is. I mean, maybe somebody in the audience knows what Kid Cool is, but I kind of doubt it. But you can still see there, like vastly different from like just if we had a Mario level or anything like that. Okay, so with that, I'm done with transfer learning. And I'll say why in this slide. We have some problems, as Russ already sort of alluded to. One is predictability, right? So we can fine tune or use other kinds of transfer learning approaches I didn't get to, but we could also use like a domain adaptation. There's some zero shot stuff we could do here in order to get things that are out of distribution. But it's unclear how actually beneficial that is, because it's very unclear what's going to happen, right? If I train a little bit over on this one or a little bit over on this one, what happens? What do I get out of that? That's very unclear right now. Similarly, to specifically Ross's point, controllability is a huge issue. If I want a particular thing, it's not clear how I get a particular thing from a particular data set or from a particular source and target model. So while there's a lot of transfer learning research, there's very little on achieving like partial transfers that could represent like novel domains. So there's just not enough here for me to talk about it more in depth, but it's an interesting area of open research. With that, let's talk about the second one of these, which is combinational creativity, which I will introduce a bit because this is a little bit weirder. So what I want everybody in the audience right now in their own heads to do is I want you to invent a brand new animal. I already did this trick with the PCG grad seminar, so everybody in it from there already knows what this is. So almost definitely what you just did if you invented a brand new animal is you took features from existing animals and you smushed them together, right? This is combinational creativity. It's also referred to as conceptual combination if you're a cognitive scientist. It is a thing that human brains are really, really good at doing very fast. It's one of the things that we do when we're trying to be creative, right? There's a lot of computational models of it. So I'm going to go over one very popular one just to start us off. This is referred to as conceptual blending. I stole this example from Joseph Guggen out of MIT. So on the left here, we have what's referred to as an input. This is really just like a graphical representation, like a way of representing knowledge, right? So we have a resident who lives in a house on land, right? Then it's the concept of living in a house, which I'm sure many people here do. Then we have a passenger who rides a boat on the water, right? It's the concept of riding a boat on the water. Now, maybe that's a little bit harder here in Edmonton, but we've got that ferry. So maybe some of you experienced something like that. And we can do a conceptual blend, smushing these existing features together to be able to get a resident passenger who rides and lives in a houseboat on the water, right? So it's a way of getting a novel something out of existing data, right? And it specifically does this sort of smush. And specifically, this is the Ficonian and Turner's four-space theory. We basically take our two inputs, we smush them together into some sort of latent space where they have the same sort of representation. We can actually match them together. And then we project them down into some blend space that we actually care about, right? So you can do sort of arbitrary blends as long as you can do a matching of them in your generic space. That's the only requirement in conceptual blending. So let's actually look at a case that's more similar to what we've been talking about so far. So these are two Bayes nets. This is some of my PhD work, so very long time ago now. But we have these two Bayes networks. These two different Bayesian networks can be used to generate out Mario levels, right? And these two kinds of Mario levels. So we have this like castle level over here on the right, and we have this sort of above ground level over here on the left. Now, this doesn't look a lot like the graphs from the example I just gave you with the houseboat. So we're going to transform them. We sort of simplify them into something like this. It's still a Bayes net, but it's way simplified over what we had before. We got rid of most of the probability distributions. We only keep like the maximum probability distributions. Once we have them in this representation, we can just run classic conceptual blending on them. And we can smush these two graphs together. That gives us this graph. And we can use that to generate out. And we can get entirely new kinds of levels that we couldn't get before, right? This is like an above ground castle level, which if you know anything about Mario, doesn't exist. Or here's another example, which I quite like. This is like an underwater castle level, which is a pretty fun concept that, as far as I know, does not exist within Mario at all. So it's a pretty cool thing to exist. Problem, we don't always have graphs, right? We can't always represent our information as graphs, as nice as that would be to always have knowledge graphs. So what do? Well, now we get into some of the work from my postdoc, Anurag Sarkar. We can actually learn the blend space. So VAEs, which I brought up earlier, are actually pretty nice in terms of learning a latent distribution, right? And if we learn a whole bunch of latent distributions for a whole bunch of different things, VAEs naturally allow us to interpolate between learned distributions, right? We can say what's in between these two different pieces of this learned distribution, right? So I use this cool concept of latent combinational blending, where you basically learn your latent space, you learn your blend space, and then you use that to like smush together existing things. So this is, again, sort of game levels here. You have your data set of K games. You have your latent variable model. This is your like learned blend space. You're going to take your latent space, smush it together to get your blended design space, and then get some outputs from that. So here's two example outputs from that. We have, I forget what all this was. It was just on the screen a second ago. This is like Mario, Mega Man, Legend of Zelda, and a fourth thing I don't remember. But there's a bunch of different stuff in here, right? And you can get wildly different levels that don't look like anything else that we've seen before. Now, are they good? To Russ's question, well, that entirely depends on your subjective sort of determination of these things. We'll get into how you can actually guide this a little bit more in a second. I should note, quick as an aside, just because I think the work is really cool, you can also use this for game mechanics, right? So we can have the same sort of like latent embedding for things like jump mechanics for platformer games, and then we can interpolate between the jump mechanics in the same sort of way, which is pretty fun. Now, everybody in this room probably knows about deep neural networks, even if you don't know them by that name. Maybe you only know them as AI or large language models now. But you might be thinking to yourself, well, hold on for a second. Matthew said we didn't always have graphs, but traditional blending presumes we have graphs, and deep neural networks are graphs. Isn't there something we can do with that? That's a really good intuition if you were thinking it, because that's exactly what we're going to do. But first of all, we have this other sort of combinational creativity. I didn't get into it. Conceptual blending is the most popular kind of combinational creativity, but it's not the only one that exists. There's a bunch of these. This is a matrix-based one, and it's pretty simple. We're basically going to assume we have some set of features. These are the Fs here. Those are like the smiley faces. And then we're going to have these alpha. This should be alpha. Sorry, it's A here. Alpha filters that tell us what are we going to grab from each of our features. We're going to smush those together and we can get some output. It's very simple. But this is just assuming arbitrary matrix representations. And if you know anything about deep neural networks, you can represent them as arbitrary matrices. Hey, isn't that nice? So we can do all kinds of weird stuff with this. But before we get to that, a real fun little example, since we've been in the game domain real quick, I just wanted to mention this. We had this like fun example where we learned whole models of entire games of the entire piece of software for Mario, Kirby, and Mega Man. And then we could get, oops, I have to click, my bad. We can get like a full output game like this. So this is a game where all the level design, all of the game mechanics, everything except the coloration and the playing, that's me, was done by sort of smushing together these existing games. So that's just a fun little aside. But let's actually talk about this, right? So if we're going to do this sort of conceptual expansion with deep neural networks, we basically can take existing matrices, like weight matrices, say, for example, for classes, and we can smush them together. And to Russ's question, I said we get back to it. What we can do is we can actually optimize how we do this combination, right, towards particular goals. So if we have like an evaluation function or a value function or however else you want to encode your notion of goodness, now we can directly optimize based on that. And this lets us do all kinds of cool stuff. So for example, we've done this with image classification models. So can I smush together like the representations, learned representations for dogs and cats in order to approximate a learned representation for a fox, having never seen a fox before? Yes, it turns out you can. Can we do it for generating fox images? Well, sort of. This was back in 2018 before we had the image classifiers or image generators that we had now. So these are with GANs. But these are GANs that have never seen a fox before. We literally had a GAN for generating cats, a GAN for generating dogs. We smush them together with a discriminator that has seen images of foxes and basically use that to optimize to say like, okay, make me something as fox-like as possible. It does a decent job. It's not great, but it's decent. You can also use this for wildly different now, financial programs. What? Yes. So let's say, for example, we have a situation where we have an individual and we want to project how, if they go under a certain financial program, what they're going to look like after some number of years. This is some work with Service Credit Union, and notably, we have no data on the second phase for this individual, really. We only have information for other individuals. So what we did is we used Monte Carlo tree search in order to optimize this sort of combination. We have this information for all these other individuals. We're basically going to recombine all that information to those other individuals to approximate this individual, right? Represent a person as a combination of other people, basically is the intuition here. We train an initial model, represent our initial model as a conceptual expansion, search the space of conceptual expansions according to the following heuristic, which is this one, which is basically saying how well do we perform over the period we know we can see this person, and how well do we perform in the area that we can't see this person, but we can see other people, right? And then we select the final model according to similarity to other individuals on this secondary task. If we look at performance here, this is loss. I can't give you the exact values because of fund, service, credit union, my tax, NDA stuff, but I will just note that like the difference here is in the like millions of dollars. So even small reductions in numbers here is very good. And notably, while in the blue there, that's the entire data set, we just do sort of okay. On outliers, this approach is like wildly better than anything else, which is really exciting. We can also use this. Oh, sure, go ahead.
How we go for the financial status?
Financial status, financial health. Sort of. I can't go massively into detail here. It's a representation of their financial health. They are wildly above or below the sort of mean, above the first or third quartile in terms of this representation of financial health. because let's say the people who are wildly above, these are the people with the most money. And so it is particularly beneficial as a financial institution to be able to perform really well on those people. Okay, anyway, so let's say Iranian folk music, or that should say folk, not folks music. We can also do the same sort of thing there. So this is work out of my recent MSc student, Anahita Dosti. This was looking at recombining existing music models for generating things like pop and rock and things like that, but for Iranian folk music. In terms of test accuracy here, we can see the performance here, the average, right? We're doing quite a bit better than sort of other sorts of transfer learning approaches that you could use. We had a small set of Iranian folk music in this case, right? That you could use to optimize, but not always super consistently. We can take a look at some. No, this is test accuracy. So over test songs that we didn't get to see during optimization, how well does the model actually predict the actual chord progressions, the actual note progressions? Does that make sense? We have exact ground truth in this case, yes. So accuracy in this case is just accuracy. This is saying that we're roughly 5% better than fine-tuning the last layer on these. But 5% is a massively different thing in terms of what that actually qualitatively sounds like in music. So we can take a look at like this MIDI representation here. The exact representation here doesn't matter so much in terms of like what this would actually sound like. But the thing I want you to pay attention to is the sort of the length of these notes and the sort of how wide or how high across we are dealing with here. So if we just use music VAE, which is pre-trained on a data set of like rock and pop and jazz and soul music and things like that, things that are very common to find in MIDI representations, you get an output like this, which is not particularly good, as you'll see in just a second. If we try to just train music VAE, which is a massive model on our very small amount of Iranian folk music, we get something like this, which is also really bad. This is basically random in terms of the way that this sounds. Then we get this. This is if we fine tune all the layers of music VAE. So it previously knew about rock and pop and things like that. And it basically, we have like posterior collapse. It has this catastrophic forgetting thing. It does not do a very good job, right? So then fine tune the last layer. This is where we actually start getting decent performance here. So this is closer to the sort of thing that we would like to see. We have sort of like shorter notes, but they're all sort of like clustered, as you can see in this like zone up here at the top, because again, we have this problem of like, Iranian folk music was out of distribution for music VAE originally. It doesn't actually do a particularly good job with it. And then finally, the CEM-CTS model does the best job in terms of the sort of spread of notes that we would like to see and the differences between them. We also have these metrics for musical quality. These are sort of based on some experts, and we do the second best compared to the Iranian folk music data set. Go for it. It's optimizing the combination. Yep. It's like a search. Your objective is to optimize the combination. So it depends on the value, right? I can do a quick, I don't know if people can see in the back. I'll right up here towards the top. So let's say we had our original model here. This is our original model. Doesn't really matter what that's for. This could be arbitrary, right? So this could be for music generation. This could be the financial health things. This could be images. It really doesn't matter. It could be anything, right? But this original model is able to do something. Then in terms of running MCTS, what we're going to do is we're going to do a series of rollouts, right? If you know RL stuff, you know what a rollout is. We're going to do some sequence of steps here in terms of stepping into the future. The changes here are not changes in terms of a position. These are changes in terms of models. So we're looking at alternative models, models that are like one step difference from this. This is not using backprop because backprop with the data that we have would not work. It would lead to the same sort of problems that we see with fine tuning directly on over the data. So instead, this is directly changing the weights. This is closer to like neuroevolution, if you're familiar with that, where we're going to use like a genetic algorithm. We're going to update the parameter weights based on that, for example, right? So what we do is we make some number of changes according to our maximum rollout length, and then we're going to backprop up those values, right? And then we're going to keep doing this. We're going to keep doing rollouts and keep on getting values. And as we keep on doing this, we're going to be updating the values of these nodes. And that means that we can keep exploring in good parts of the space. The reason why MCTS is particularly good is because the sort of representation that we have here tends to be extremely spiky, right? So if we have some sort of like way of we could represent the entirety of the space of all neural network models as a single line, which would be a wild thing that we could potentially do. But we've done some sort of massive dimensionality reduction, and now we can do that, right? And we have this sort of like fitness function that I've sort of gestured at we have, right? So like for music, it could be something like, okay, I have a small set of Iranian folk music MIDI pieces. I'm going to use the accuracy on those as a metric. For something like images, we could use something like MSE or SSIM, which are like classic image representations. For something like financial performance, right? We can just get the precision, right? Et cetera, et cetera, et cetera. It's domain dependent, right? What it would look like is we'd have like massive spikes and then like nothing, absolute garbage performance. Massive spikes, nothing, absolute garbage performance. Massive spikes, absolute nothing, et cetera, et cetera, et cetera. And MCTS is particularly good at sort of like, you can think of it like a bridge, like linking these sort of like peaks to each other, right? Because of the way that you can do rollouts and then continue exploring good parts of the space. This is what we've found consistently. Cool? Cool. Okay, so this also is not a perfect approach. It has problems. It is not appropriate for all problems. So we've attempted to use this sort of approach for domains where the features are not human interpretable. Because as I demonstrated with this sort of like animal example at the beginning, it seems like when humans are around, we'd have a tendency to represent things in terms of feature representations that are particularly good for doing this sort of combination task. We seem to really like it. But in cases where we don't have these sort of human interpretable features, it doesn't tend to work super well. So it maybe requires this sort of human understandable learned features. How to optimize is unclear, right? MCTS seems to be really powerful, but it's not all powerful. And it's unclear how this can relate to other alternative optimization approaches, right? There's lots of sort of like different ways of following only certain parts of the gradient and things like that for dealing with low data problems. It's unclear how these sort of things align. Okay, so with that, I've finished covering these sort of categories. I'm going to talk about some overall takeaways, and then we'll have plenty of time for questions. So producing truly novel output is tough, unsurprisingly. There's all of these open questions around like, how can you actually do this sort of out of distribution thing? What does it even mean? How do you measure quality, et cetera, et cetera, et cetera? Transfer learning is promising as an approach, but is underexplored. Again, transfer learning tends to say, okay, I have this well-defined domain, I have this well-defined domain. I just want to do as well as possible in this second well-defined domain. What if what we want is a domain halfway in between those two domains? Uh-oh, how do you do that? How do you define that? How do you actually ensure that you can consistently get that sort of output that you want? All of this is unknown. These sort of combinational creativity approaches have this sort of strong, this didn't work, cog-sci, cognitive science, backing and success across many domains, but a lot of work remains to be done. I will note real quick, right, a bunch of people working on this research. A lot of graduated master's students have worked on this on Mohan, Samradi, and Anahita. I currently have Mashfiq, who's doing some cool stuff on this, particularly with chip design and preterm birth, which is exciting. And then Anurag Sarkar is my postdoc, who just started back in September, who's also interested in doing this, particularly for like more general game domains than what we've been able to do it for in the past. Think real quick, all the sponsors who sponsored this research.